The weather was pretty good, so Sarah was able to have a reasonable drive from Pocatello here today. But Sarah Godsey is assistant professor at the Department of Geosciences at Idaho State University since January 2012, so 4 years now. Prior to that, she had a postdoc at Penn State. She has a bachelor's from the University of Virginia, a master's from the University of Cincinnati, and a PhD in Earth and Planetary Sciences from the University of California, Berkeley. Her research interest can be summarized in 3 topics: catchment hydrology, geomorphology, and hydrochemistry. And to make that a little clearer, taken off her website, she says that our group at Idaho State University focuses on hydrology in mountain and polar regions. We're interested in how climate and land use changes may affect water resources in these areas. And just for the couple of you who may wonder what hydrology is, it is the science of dealing with the occurrence, circulation, distribution, and properties of waters of the earth and its atmosphere. So she's all about water, frozen or liquid. She has a very long list of grants, honors, and awards, publications, involvement in conference proceedings, and invited talks. She teaches a wide array of courses and mentors a long list of students towards master's and PhD degrees. And on top of that, ella tiene completa fluencia con la lengua. She's fluent in Spanish. So we're very fortunate tonight to have Sarah Godsey, and I'd like to ask you to help me join me in welcoming Sarah.
You guys hear me pretty well? All right. So thanks so much for coming out tonight. And all right, ooh, the lights come down so we can see the mountains a little bit better. This is great. So today we're really going to talk about snowpack, and I understand that that's something that a lot of you in this room think about from one perspective or another. And so I'll try to tie in a few of those different perspectives. But really what I'm going to do is I'm going to walk through a series of studies that a student that I've been working with has been working on. And I'll show some recent results and some things that are still in progress, and then I'll give you guys a hint of where we're headed. And in particular, we'll take a look at the sensitivity of some of the mountain snowpacks right around here and see how the framework that I'll be talking about might indicate what the future of the snowpacks right around this area might be. So John gave you an idea of some of the work that I do, and I just wanted to let you know I really like to dive into my work. This is me hanging out inside of a region of permafrost that had actually thawed and opened up a crack in the ground. And I hopped in it thinking, okay, this will be fun, and I actually couldn't touch the bottom, so my friends had to pull me out. Wow. So I will not be talking about any of the work that I've been doing in Alaska over the last few years today. I understand that my colleague Ben Crosby is coming in a little bit, and he'll be sharing a lot of the work. He and I have collaborated on several projects that he's been doing in Alaska. And if you get a chance to come for his talk, I highly recommend it. He's got some really cool stuff to share. The person who did the lion's share of the work that I'll be talking about today is Chris Tennant, and he's now doing a postdoc at UC Berkeley, along with Ben Crosby, Dwayne Derryberry, and Rob Van Kirk. All of these folks have been involved with the work that I'll be talking about today. All right, a little bit of context. You guys know this as well as anybody, but skiing over the last few years has not been as extensive as some might hope. Right? There have been a number of years after I moved to Idaho that have been really disappointing snow-wise. This year's looks promising with the El Niño, but we'll see kind of how it plays out. You guys have probably heard, if not seen, these exact figures that show an increase in temperatures on the left. Warming is expected to be widespread. You guys will hear a lot more about this if you attend the members' lunch tomorrow, I'm sure. The thing that I'd like to point out is that precipitation, the figure on the right, is a lot less certain. There may be more precipitation, there may be less precipitation into the future. But we're going to focus for a moment on what the effects of warming might be for mountain snowpacks. One of the possible impacts of warming, and particularly warming in the spring. Let's see, if I use my mouse here, do you guys see that? No? Okay. So, oh, there is a mouse? Does it show up on both of them? That's the real question. Yes. Oh, it does. All right. That way I don't have to move the pointer back and forth. Can you guys see that well enough?
Yep.
All right. So this is March to May temperature trends. So we see significant spring warming. And what you can imagine is that that can lead to earlier snowpack melt. And in fact, we observe changes in the timing of peak stream flows, where stream flows are peaking earlier and earlier across much of the West, though not all. And in some cases, by more than 20 days. The peak stream flows are occurring more than 20 days earlier as a result of mountain snowpacks melting out faster. Earlier than they have in the 50s to 90s. There are a number of questions, however, things that we don't understand well enough about how Western snowpacks will respond to warming. We don't know which basins are most sensitive to warming. And we don't know how much that depends on glacial history, for example. We don't know whether or not that uncertainty in precipitation might offset any of the changes due to warming. There's some interesting work that suggests that changes in winds may also impact snowpacks, and that's something that is poorly understood. I won't spend as much time talking about that today, but I have some students who are working on that problem right now. There's also a lot of complexity in terms of how snowpacks interact with vegetation, whether or not there are fires that affect that vegetation or different kinds of forest management practices that influence where there are trees and where they're not, how the canopy interacts with the snowpack that comes through. And there are some important implications for changes in snowpack that we also don't understand particularly well. If snowpacks do melt out earlier, and if stream flows peak sooner, that would suggest that during the summer there might be periods of time when streams become drier than they have been in the past. And if that's the case, that implies that there could be some streams, especially if they have very small amounts of flow right now, that could become ephemeral, that currently run year-round. We don't know which ones are most likely for that, where that is most likely to occur. In addition to that, there are also changes in the temperature of stream waters. And temperature of stream waters, for those of you who fish, you know this well, I'm sure, the temperature of stream waters influences which fish species succeed and thrive in particular streams. And so if we see warmer temperatures, even if the flows don't dry up, we might end up seeing shifts in the species that are successful, fish species that are successful in those streams. We're not going to talk about all of that tonight. This is a lot of stuff, but I wanted to give you an idea of some of the key questions that are being tackled by different people in the hydrological and ecological community. Today, I'm going to split the talk into a couple of different pieces. For the first part, I'm going to talk about some results looking at patterns of stream flow in the Salmon River Basin in Idaho. And in particular, we'll look at patterns across low to mid to high elevation zones that are rain to snow dominated. And we'll look at whether or not those patterns, how well they're represented by the existing network of stream gauges that we're so lucky to have in this country. In the second part of the talk, I'll talk about which mountain watersheds are most sensitive to warming, and discuss a framework that lets us evaluate what those patterns of snow loss might do at the landscape scale. So first, let's talk about the Salmon River Basin. This is a really neat place to do work. It's known as the River of No Return. I'm actually taking Some of the students from my watershed hydrology class this year, we're going to go back into the Frank Church River of No Return Wilderness as part of a field trip with the class. I've been raising money to help offset some of the costs so that they can come along, and we'll be doing some studies that build off of work that I've done there already, looking at how trees use water across the rain to snow transition. So the River of No Return drains about 14,000 square miles in central Idaho, and it's got a 7,000-foot elevation change from its peaks down to its outlet on the Snake. It carries a lot of water, and it's really important for recreation and for sockeye salmon runs. This plot is a really interesting plot because it shows us what the patterns of elevations are at these sites. And so across the bottom here, you'll see the name of a whole bunch of watersheds, and then elevation shown here on the y-axis. And each of these plots, these are known as spindle plots, show us how much of the area of the basin occurs at a particular elevation. And so if it's really narrow, then there's not much area that's represented at that elevation. If it gets really wide, that's where most of the area of the basin is located. And so what you can see here is that some of them have a wide area all the way across their entire width. And so that suggests that they've got about the same amount of area at all elevations, whereas some of them have really narrow needles coming out from the edges and then a wide area right in the middle, which would be like walking up to a plateau where most of the elevation is at a single, or most of the area of the basin is at a single elevation. So you can see that from one place to another, there's a lot of variability in where the bulk of the area is in a watershed. And that depending upon where we are within the elevation range, we go from rain-dominated down here through a mixed rain and snow transition zone up to snow-dominated elevations. But you can see that there is some portion of the watershed, of most of these watersheds, that sort of crosses those bounds. So that even though these are rain-dominated, some of their area falls in that mixed rain and snow zone. And if we look at the entire Salmon River Basin here, if we look at the entire basin, it spans all three zones. That makes this a really great place to look at the possible impacts of a phase of precipitation, whether it's falling as snow, as mixed rain and snow, or as rain, how that influences streamflow patterns. This is probably not going to be surprising to most of you. So we've got here an average year across the x-axis here, and then we have two plots, one that shows the percent of annual stream flow on the bottom and the percent of annual precipitation on the top. And then we have three lines. These lines show us snow in the dark blue, then mixed rain and snow in the light blue, and rain in this grayish color. So we can see that rain-dominated areas get their precipitation a little bit later than the snow and the mixed rain and snow dominated elevations. But there's not a huge difference. Of course, when we look then at stream flow, we can see that the stream flow comes out much earlier for rain-dominated elevations than it does for either the mixed or the snow-dominated elevations. Those guys get their stream flow much later. And that's related to what we saw earlier, that shift in the timing of stream flow as there is the chance for warming. What other things do we notice when we look at patterns of stream flow across elevation? One of the most interesting things that we noticed is when we looked at stream flow for each of these sites and we plotted up, what's happening on average, and then what happens only every so often. The dots represent things that fall into the category of extreme events. So those aren't occurring very often at all. And the dots that we see at the rain-dominated elevations occur on the low end, whereas the dots for the mixed rain and snow predominantly fall on those high stream flows. So we see a lot more extremes of flooding at mixed rain and snow-dominated elevations, and a lot more extreme droughts at rain-dominated elevations. We also wanted to see whether or not the range of stream gauges that we have available to us do a good job of representing all those different elevation bands, all those different processes that are happening. And so what we did here is we looked to see, okay, how well is the Salmon River flow at its outlet? How well does it match the flow, how well does it match the flows at snow-dominated and mixed rain and snow and rain-dominated elevations? And this plot lets us know where along the range of time those peaks best match up. And so when it occurs at 0, we see a match between the peaks of flow at snow-dominated and mixed rain and snow that match up with the peaks of flow at the Salmon River outlet. Whereas what we can see here, by the peak of this gray line falling at around -50 days, what does that mean? A peak at -50 days means that rain-dominated sites end up having their strongest match to the Salmon River Basin. The flows that occur 50 days before the Salmon River Basin peaks are the rain-dominated sites peak about 50 days before the peak that we see at the Salmon River Basin. So that means that if we're only measuring flows at low elevations, that we might do a poor job representing what's going on at our highest sites, and vice versa. If we think that our Salmon River Basin, which is integrating all 3 of those elevation ranges, is going to do a good job letting us know what's going on in rain-dominated sites, then we're deluding ourselves. We actually need to measure what's happening in rain-dominated sites to be able to understand those settings. So I hope that that gives you a little bit of a sense for, in a site like the Salmon River, where we have rain-dominated to snow-dominated areas, not unlike most of the western US, that there are some patterns that we can observe. And that lets us evaluate, or lets us move towards this second part of the talk, where I want to explore which watersheds are most sensitive to warming. And if we can figure that out, then what might be potential patterns of snowpack loss at the landscape scale? So first, I'm going to talk about this in a pretty theoretical way, and then I'm going to apply it to the entire western US. So all of the watersheds in the western US. And so hopefully you guys will stay with me through some of this theoretical part, and then we'll get to see how it comes out and gets applied to a whole bunch of watersheds throughout the region. The basic idea is pretty simple. We have a relationship between snowpack and elevation. Snow's more at higher elevations usually. We have a distribution of elevations on the landscape. Some of our area is located at low elevations, some at mid, some at high. And depending on our watershed, the amount of the area that's at different elevations varies. If we put those two things together, we should be able to describe how much snow, in terms of the amount of water in that snow, how much snow there is in any given watershed on the landscape. So we'll come back, we're going to start on the left side here, where we're going to just take a look at what is the relationship between snow and elevation. There's an acronym that I'm going to use a lot in here, and hopefully it's not a totally unfamiliar one, but if it is, I want to make sure that I define it for you guys. we're going to talk a lot about peak snow water equivalent, or peak SWE. So that would be if I took a column of snow from a snowpack and I melted it down, it would be the amount of water that I would get from that snowpack. And so that integrates the density of the snow. So if I had 2 feet of powder versus 2 feet of a dense concrete snowpack, that would be a very different amount of water that would be held in that snowpack. And so this is a way of taking into account differences in density. So I'm going to talk a lot about peak snow water equivalent. And one of the coolest things that we found out was that when we plotted up the peak snow water equivalent for a whole bunch of different watersheds throughout Idaho, we found that there was a single curve that fit that pattern for almost all of the watersheds that we looked at, for almost every single basin. And for those of you who like to know something about the mathematics of it, it's the Richards function. That part doesn't matter too much, but what matters is that there's a part where it's pretty flat at the bottom, and then it turns and goes sharply up, and then it flattens out again at the top. So there's this mathematical way of describing how snowpack increases with elevation. And it turns out that it's something that we can figure out for any given watershed as long as we have a little bit of information about that site. So what we did is we said, okay, we're going to simplify all of this cloud around that line. We're going to take this single line, and then we're going to try something really interesting as a way of simplifying what the possible impact of warming might be on a snowpack. So what we did is we said, okay, you know what? We're going to shift this line over to the right. In other words, we're going to say we're going to have to be at higher elevations in order to have snow. That otherwise, at those lower elevations, those are going to be the ones that are going to shift over to rain. That's not a totally crazy idea. We know that there's somewhere along the range from the bottom of a valley up to the top, usually we find our snow line. And so we just said, hey, what we're going to use is we're going to assume that we have the same shape of that snow elevation relationship, and then we're going to shift it over so that we have to be at higher elevations in order to have the same amount of snow. All right, so that's the snow elevation part of this theory. The next part is describing how the elevation of watersheds varies from place to place. And so we can have an area where we have a watershed where most of our elevation is, most of the area of our watershed is at low elevations, like this dotted line here. One where most of it is at mid elevations, like the solid line, or this dashed line where most of our elevation or most of the area of our watershed is at high elevations. And you can imagine that that would make those 3 different watersheds respond really differently to warming. That high elevation one is going to be really resistant to any warming because most of its area is way up there. And so even if it warms a little bit, it's still below freezing, snow is still falling. Whereas these lower elevation watersheds might have more rain already, and the little bit of snow that they get might just disappear. So if we look at how elevations vary across a whole bunch of watersheds, and we look at it in terms of what fraction of the area is below a particular elevation, we get this spaghetti thing over here. That's not particularly useful, right? There's a whole bunch of variety in how elevations vary from place to place. We saw that with the spindle plots in the Salmon River Basin as well. I wanted to show you guys a couple of examples from around here just so that you could get a sense of what this might look like, because I'm just going to use these from a bunch of other places. So this is the percent of the watershed area that's below a given elevation. And so what we can see is that most of our, let's see, we get up to about 1,800 meters We have only 20% of our basin area below 1,800 meters in these basins. And then by the time we get up to 3,000 meters, we have almost all of the basin area included. There's a little tiny bit that's up there above 3,000 meters. But you can also see that there's a little difference between these two sites, that the Snake River Fall Creek curve increases more sharply. So there's more of the area in this range from about 2,000 to 2,500 meters down here than there is for Flat Creek. Flat Creek has a little more of its area higher up. You probably know this if you're walking around in an area. You would start to feel it, right? You would start to see curves and steep parts on this plot in similar places to when you're hitting, steep parts and flat parts of a trail that was going up this. But it's integrating over the whole area, not just one trail that takes you from the bottom to the top. This is the most math of any of the slides, so hopefully it's not too much. But the thing that is really cool about this, this work that we've done is that we can describe how area varies with elevation with just 3 parameters. 3 parameters, and one of them is simply, what's the average elevation? One of them is, how variable is the elevation around that average? And then the last one is, how much of the elevation, or how much of the area of the watershed occurs just at really particular extreme elevations? So how much is up on kind of rocky knobs at the very top, or how much is it just a very little bit down in valleys? So we've got 3 key parameters, just the average elevation, its variability, and then this one actually ends up not mattering too much. So how much is in the tails of the distribution. And then we compared this to about 3,000 watersheds. We tried to fit the best parameters we could to 3,000 watersheds throughout the western US. And it turns out that we did a really good job of fitting these. You can see that there's a little mismatch between our line and these gray bars underneath. And that mismatch there is usually around 3%, but it meant that we were actually doing a pretty good job. We could represent the patterns that we saw most places with just these little parameters, which meant that we could come up with a way of representing a whole suite of watersheds throughout the whole possible range of elevations and the possible range of variability in those elevations. So we started out with all of the observations that we made, and then we generated even more fake watersheds, synthetic watersheds, so that we could test out whether or not this worked and how sensitive each of those synthetic watersheds would be. So this is really similar to something that's known as a Monte Carlo simulation. That name might sound familiar to some of you. This is a Monte Carlo simulation because it's used in gambling, right? You come up with a whole suite of possible outcomes, a whole suite of possible rolls that you might make or card combinations that you might have, and you go through and you see which ones are most likely to occur and which ones aren't. So we did that same approach with these watersheds. Finally, we took that whole suite of synthetic watersheds and those patterns of snow, and we put them together to see which watersheds had the most snow. So we could apply that range of snow across elevations to the elevations themselves to see how much snowpack we had. So if we applied this guy to our lowest elevation watershed, we might only have 400 millimeters of snow water equivalent. Whereas if we applied that same snow elevation relationship to our highest elevation site, we could end up with twice as much. We could end up with 800 millimeters of snowpack in that watershed. So then we wanted to know how will those watersheds respond to warming? And so to do that, we figured out the current snowline elevation, and then we started to shift it up. And as we shifted that snowline elevation up, it meant that we were applying this curve to these elevation bands to generate this amount of snow water equivalent at each site. And as that snowline elevation went up, we would intersect less and less of the watershed area with the region that received snow. What does that end up looking like? How can we figure out how much snow we would lose through that process? Well, we would take our snow elevation relationship, we would shift it over, and then we would apply it to our elevations on the landscape. And so if we started out in our current scenario with this upper line here, including the darkest blue, we might start out with 500 millimeters of precipitation. We then would shift our line over so that we could see that we would have our peak snow at about 380 millimeters of snow. That would drop us down to this light blue line. And so the difference between these would mean that we would lose about 120 millimeters of snow water equivalent through this process of warming. So we did this for a bunch of different warming opportunities. So we looked at 1 degree all the way up to 5 degrees of warming. And this is a plot showing us the average elevation, right, the middle point of our watershed, and how much snow water equivalent we lose. So we can see that for the 1 degree case of warming, we have our peak losses at watersheds that are centered around about 1,200 meters. So at around 1,200 meters, we have our largest losses. It's only about 50 millimeters of snow water equivalent, so it's not a ton. But as we shift to our warmest case, our 5 degrees of warming case, we see that we've shifted slightly to higher elevations, where our peak losses are around 1,600, 1,700 meters. And our losses have increased rather substantially. We're all the way up to around 225 or so millimeters of snow water equivalent that we've lost. So it's a pretty big increase in the amount that's lost, and it shifts the elevation that's most affected. So the degree of warming matters, and the location, the elevation of the watershed matters. Those two things together are a really simple way of evaluating how sensitive our watershed is to warming. There's another way that we could look at this, and this one might be more intuitive, so I'm going to throw it out there, and you guys can tell me whether or not it is. But there's also the idea that we could figure out how much of the area of a watershed is actually above snowline. And so that means that first we need to know where is snowline, which sounds like it should be a really easy question to answer. Where is snowline? Well, it's a place that you see, the snow has fallen above this line, and below that line we don't see any snow that's accumulated, and so that's where rain was falling. Except for we know that that varies over time and keeps moving up as the snow melts. And so what do we do to actually represent the snow line? On average, we decided that we would say the snow line is the place where there's snow at least half the year. So that's a pretty strict definition. You might say, hey, that we're going to have a snow line that is, that there's snow at least half the winter, or something like that. But this is what we chose. So we chose a snow line is defined as the elevation at which we find snow half the year. And then what we did is we said, okay, here's the area that's above snowline right now. And if we warm, there's going to be an area that we lose, an area that was above snowline before, but is no longer above snowline. And the difference between those two is this red zone. And we'll divide that by the area of the whole basin, just to see how much of the area of the basin is losing snowpack. So how much of it was above snowline before and is below snowline now in a warming scenario. So this is the amount of loss from 0% to 100% of the area above snowline. And so this is going from 1 degree of warming again, all the way up to 5 degrees of warming. And the location of the watershed, the center point of the watershed, is shown on the x-axis again. So this is really similar to the snow water equivalent figures that we were seeing before, but there are a couple of key differences. One is that we can see that we can have certain areas, particularly at mid-elevations, where we can have up to 100% area above snowline loss. At lower elevations, that doesn't happen because mostly there wasn't that much area above snowline to begin with. And so even though it's all lost, it was only 10 or 20% of the watershed, and so that's why it shows up as a small amount of loss. We also see up at the highest elevations that the area above snowline loss drops down to really small amounts again. It's down to, you know, 10 or so percent, and even less as we go up to those highest watersheds. And that's because those are regions that have very high elevation snowpacks that don't reach the threshold for actually thawing at least half the year. So this means that we can actually predict, if you buy all of this so far, that we can predict how much water we could lose from a watershed on the basis of two simple things. One, the shape of the watershed, what's its elevation distribution, and two, how snow varies with elevation across that watershed, which is pretty cool. Those are things that are surprisingly easier to measure than a lot of other things that we have access to. There's only so many snow-tell sites around the western US where we're measuring snow water equivalent at those places. But we actually have flown LiDAR, so we've acquired really detailed elevation data at a lot of watersheds. And we have decent elevation data for the entire US. And so we can start to say, hey, if we know this information about these different watersheds, we can figure out which ones are most likely to be really sensitive to warming and which ones are likely to be very resilient. So we decided that we'd go ahead and apply this to watersheds throughout the Rocky Mountain region. And we looked at 4 ecoregions in particular, and these are EPA ecoregions. And so the same colors will show up over the next few slides. So we've got the Idaho batholith over here, and it looks kind of like a salmon leaping up out of the water if you look carefully. Here's its mouth. And then there's the Middle Rockies, so that's the unicorn. And then there's this little jaunty fellow up here, that's the Canadian Rockies, which are actually in the US, so sorry for the confusion on that one. That's just the ecoregion name. And then finally, the pink blob over here is our Northern Rocky ecoregion. So we'll come back to each of those. We're going to use this same technique that we just talked about and describe the elevation and the snow patterns across each of these watersheds. And we can see all of those sites summarized in just this one slide. So this has got a lot of information on it. We've got the same thing here that you've seen a lot of other times, the elevation across the horizontal axis, and then we've got the area. So this tells us how much of the elevation, or how much of the area of the watershed is in each elevation. And then across the top, we have the pattern of snow as it varies with elevation. And so you can see that it is sort of flattish at the bottom and rises up. This is a key distinction when you look at all of these places from what we talked about before. You see that in some places, it starts out low and goes up and sort of tops out, like in the northern Rockies. However, there are some places where it hits a peak and then it rapidly seems to decrease. There's a lot of variability at those high elevation sites. We're going to come back to that at the end. But what we did for the purposes of this analysis was to fit a line through that, to use that information at those highest elevations. Most of the watersheds didn't have too much area at those highest elevations, so it doesn't affect our outcome very much at all. But there's some really interesting stuff that's going on. So hold on to this turning point, this sort of peak and then decrease for a little bit later. So we've got our patterns of how snow varies with elevation and our patterns of how area varies with elevation. And then we have our opportunity to see how those patterns of snowpack with elevation will change with warming. And so very similar to what we just did in the theoretical case, we applied this to each of these regions where we shifted the point at which they start to rapidly rise, and then we kept the elevation at which the peak snowpack occurred the same. And so that means that, for example, in the Canadian Rockies, it's shifted over enough that we don't hit the same peak snowpack. We have a much lower peak snowpack at those same elevations because we've shifted our whole curve over. So that's due to warming. We're assuming the same amount of precipitation. It just means that a lot more of it's falling as rain instead of falling as snow. So we take all of these curves and we apply them to the areas of all of the watersheds to start to see the patterns of absolute snowpack loss on the left and relative snowpack loss on the right. What do I mean by that, and why am I showing you both of them? Well, the absolute loss is just how many millimeters of snow water equivalent have we lost. Have we lost, in this case, 100, 300, or more, up to 500, half a meter of loss of snow water equivalent. Well, that will vary a lot depending on how much snowpack we had to begin with. And so that's why I'm showing you the relative losses as well, from 0 to 100%. If we didn't have a lot of snowpack to begin with and we lost 200 millimeters, that's a pretty big deal. That could be 100% loss. Whereas if we had a whole lot of snowpack, a 200 millimeter loss might not be that big a deal at all. So we've got these patterns, and they look really similar to the patterns that we saw earlier, which is consistent with the way that we're applying this model. What I really wanted to know was, what does this look like on the landscape? Which places are actually more sensitive and less sensitive? So here's our map in the lower right-hand corner of where all these places are. And then here we have a map of our absolute loss and our relative loss for just a 1 degree Celsius warming. And so there are a couple things to keep in mind. Blue means that a site is resilient, and red means that a site is very sensitive. And there can be a combination. So a site that is, and I sort of feel like this is like red fish, blue fish, 1 fish, 2 fish, but we've got blue on both sides. We have a low absolute loss and a low relative loss. That means the site is very resilient. If we have a red-red scenario, so let me, in the nose of the fish. If we have a red scenario, that means that the site is losing a lot of snow water equivalent and it's losing a lot of its snowpack. So there's a large relative loss. It might be, 60% to 80% of the snowpack loss, as well as a large amount of loss. And then we have interesting situations where we have blue and red, where we have a small amount of absolute loss, but there wasn't much snowpack to begin with. And so we have a large relative loss. So even though we didn't lose too much of our snow water equivalent, we have a large, the snowpack itself is much smaller than it used to be. So that's how this sort of plays out and can be useful. So maybe let's zoom in on the area where we're at and take a look. What does this mean? Well, we see this color where we have red-ish colors for our absolute loss and bluish colors for our relative loss around here. So that means that we're losing some. In this case, right, we're losing somewhere around 50 millimeters of snow water equivalent. But that doesn't have a large impact, relatively speaking, because snowpacks are larger here. That might not be the case, for example, in the Idaho Backlit. So this would be a region that would be relatively resilient to changes in temperature. So I want to come back to what I mentioned before about that tip where we started to see things coming over the edge and starting to decrease again at highest elevations, where the snowpack didn't continue to increase to the highest elevations. Well, that can occur for a whole bunch of different reasons, right? You guys, I'm sure, can come up with a variety of reasons for that. But one of the things that is the most interesting to me is some work that was done by Charlie Luce out of Boise, and suggesting that at very low temperatures, right, below 0 degree winter average temperatures, that snowpacks are very sensitive to changes in temperatures. But as you get to warmer winter temperatures, they're much more sensitive to the amount of precipitation that's coming in. So that suggests that there could be a pretty serious limitation to the model that I just showed you at highest elevations. That if there's more snow that can be wrung out of clouds at those highest elevations, if, in fact, those places that have the most precipitation get a little bit more precipitation because the air is warmer that's coming in and it can hold more vapor that can get wrung out in the mountains, that those are areas that really need to be understood particularly well. And so that's some of the work that we're working on right now, and I don't have results yet to show you, but it's a really interesting area. And then the other one that is particularly interesting occurs right in this zone where we have the rain to snow transition. That rain to snow transition is really important because it means that moisture can get blown around. The precipitation that falls doesn't necessarily stay, right? It's not distributed really nice and evenly all over the landscape. Instead, it can get blown around and have patches that are much wetter or much drier than others. And so we're spending some time trying to understand better what's going on in that zone as well. And so with that, I want to thank you guys very much for your time, but also all of these funding agencies who have helped to support this work. And I would love to take any questions that you guys have. Thank you.
Synthesize, if you will, a variation in the
see if I can remember.
Given that the precipitation remains constant, that some of your precipitation is falling as frozen and some as liquid,
Yeah.
how does that affect the recharge characteristics of the aquifers? How would you expect it to affect the recharge characteristics of the aquifers?
Those are great questions. So, okay, so the first one is, could we find other places where we might be able to compare this? There are a handful of places where we might have enough data to actually be able to do that. The other approach that I've seen some people working on, and just was at a conference where I saw some people presenting on this, was to look at the information that we have from streamflow to try to back out that as an integrated measure all the way across the rain to snow transition to see whether or not the precipitation that we think we're measuring at the places that we're measuring it actually pops out at the stream gauge, or whether or not we're off by a certain amount. And the work that I've seen suggests that we actually have a little bit more precipitation falling at the highest elevations than we have thought previously. And so we're adjusting our models accordingly. So let's see. The second question, remind me just.
Aquifer recharge.
Aquifer recharge, right. That one is more complicated. So there's a number of factors. So precipitation phase matters because it affects when that water is available to infiltrate. The other thing that matters is the property of the ground. And so you guys know this as well as anyone. If you have a really cold spell come through before you have a snowpack, your ground will freeze and it will not take in water that's coming through. Whereas if you have a snowpack that develops before the air temperature gets too cold, then you can actually maintain the infiltration capacity of your soil for a lot longer, and that can influence the availability of the ground to absorb any melt or rain that comes along. And so that's a long answer to the question of that you're asking, which is essentially it depends. If the ground's frozen, then you're going to have a heck of a time allowing that water to infiltrate. If the ground stays thawed, then rain and melt can both infiltrate reasonably well.
Yeah, I'm going to ask a question that may make you throw your hands up and walk out. Yeah, what is a snowpack?
What?
What is a snowpack?
What is a snowpack?
Is it synonymous with a snow line? How can it fall as rain? Is it something that you measure in terms of time and depth?
Yeah, so I think of the snowpack as whatever precipitation that has fallen as snow or has fallen as rain onto snow in some cases, whatever that accumulation of water is above the ground surface. And so in some senses we could talk about storage of water in the subsurface, but we also talk about storage of water on the surface in either glaciers or more commonly in seasonal snowpacks. So the difference between a glacier and a snowpack is that, in the way that I'm talking about it, is a snowpack is melting seasonally.
So if you are saying, as they did on the radio today, that the snowpack in Wyoming is 80% of normal,
Yeah.
are they going to the same spot every year?
So what?
Or are they looking at SWE equivalents?
So they're looking at SWE, they're looking at snow water equivalent, and they're going to the same spots. So the NRCS goes out and they've chosen a number of spots where they do, and I'm not sure in that particular report, but I'm gonna guess that it's, they go to a bunch of sites that are snow telemetry sites, which means that they've got essentially like a water bed with antifreeze in it, and a sensor at the bottom that measures the pressure of snow on top of it. And so it's the weight. And so it doesn't matter if it's a light powdery snow or really heavy snow, it'll measure the same weight, that same pressure for the same snow water equivalent.
So that's how you standardize that definition by the...
And so they've probably, again, I'm guessing here a little bit, but they're comparing it to either a 20 or a 30-year average. So from, say, 1980 to 2000, maybe, that's what I'm guessing, or sometimes 1980 to 2010. They say that's the average, and we're going to compare to that period. If they install the sensor after that, then it'll be a different time range. But when it's 80% of normal, usually early in the season, those numbers are highly dependent upon whether or not you happen to have one storm or not. Later in the season, they're a little bit more meaningful. So, does that help? Yeah, great.
I'm glad you didn't walk out.
All right.
If you go to the snowtail sites and look at some of them, they're very informative, and you see exactly what you're talking about.
Yeah.
You watch the snowtail graph for, say, for this year versus that long-term average, and you can see what's happening.
Yep.
If you go there right now and look at the snowtail graph from Targhee and the one from Phillips Canyon or something like that, Targhee is going up like a rocket because they're getting dumped on. And that's exactly what you were talking about as to whether or not you had a peak storm.
Yeah. So if you look at these curves, and you could even, it's online, you can pull this up, real-time information, and anybody can. And if you are, if you're careful as you're driving up and over Pine Creek Pass, if you keep your eyes open, there's actually one that's very close to the road there. And I take my students there too. So, and so we go out and measure the snowpack there. But what you'll notice is that always, every year, the current year's snow water equivalent curve will always be jagged compared to the average one. And that has everything to do with when the storms happen. The average is averaging over 20 years of storms that might have occurred on one day or another, and so they get smoothed out. But yeah, I don't know, I like watching those curves. Other questions? Yeah.
If you could go back about 5 or 6 slides to the slide that you had the different areas, northern Canadian and what all, and it had that wing over on it.
Maybe this one?
No, keep going back.
Okay.
Sure. I think you just went past it.
Oh. This one.
Next one.
Next one. All right. This way.
The thing that I look at these curves and it's not clear to me is the separation between the curves. So if I look at the Canadian Rocky curve, I see quite a bit of separation by the temperature change.
Yep.
Whereas in the Idaho batholith curve, there's very little separation.
So
what is controlling? How are you calculating those curves?
Yeah. So these curves, if you'll notice, there's a different amount of elevation in each of those ecoregions. Some of them vary a lot more widely than others, and so that's what causes there to be that stretching or shrinking of the distance between those. The way that we moved those curves over was simply to apply a lapse rate. So we said, hey, if there is a 1 degree amount of warming, how far over does that shift us? And so we apply that same amount to each one. Yeah.
Oh, there's one there.
Okay,
Yeah.
go ahead.
It seems like this is a really interesting approach to trying to quantify estimated losses in snow water equivalent. But looking at elevation and watershed shape seems to have a gap in your sampling size, in that most of the gauges where we have 30 or 40 years of rainfall data or streamflow data are in areas where they're developed, and there are watersheds that are shaped such and at such elevations that they don't have engaging information. How are you looking at this, taking this approach and then seeing the results and verifying them from the empirical data that are accounting for those watersheds that don't have any telemetry data in them?
Yeah. So what we ended up doing to get the snow elevation relationship was to use the SNODAS data set. That may or may not be familiar to you, but and so we took that information, which is spatially distributed snowpack, and then we used that to derive these snow elevation relationships. And then the elevation data we just have from the National DEM. And so that's how we came up with those relationships. We worked on a watershed basis. So this isn't intended to tell you where within one of these watersheds are you actually going to have snow or not. It's supposed to say, hey, here's our watershed, how much change in snowline equivalent would we expect to come out of it? Because you'll notice, I mean, you guys know this, right? That aspect plays an important role in where you actually find snow on the landscape. We're not dealing with the role of energy in this at all. We're saying that it's getting smoothed out. We actually checked to make sure that aspect was more or less represented evenly across these watersheds. And I was surprised actually by how well it worked in most places. So it's intended to work on a watershed scale, and then we applied it to the hydrologic unit code 10 watershed. So that's a particular level of watershed that's on a slightly larger size of watershed. So it's not intended to apply to these really small ones. There's not an easy way to validate this. So we can do this for the handful of watersheds as you've described where there's actually stream gauging information above dams and other impoundments and things that sort of shift the timing of stream flow. But that's one of our challenges in any sort of evaluation of warming is what do we do if we're running the experiment right now and we don't have a way to evaluate it. So I think to a certain extent we can evaluate places where there is a long enough record to try to tease that out, but it's a tricky one. So you've nailed it, one of the challenges. Yeah.
On this graph and the one immediately before, you're clearly showing or you're illustrating the reduced amount of snow water going from at higher elevation.
Yeah.
Can you briefly explain what the mechanism is to cause that?
So in some places, avalanching, wind redistribution, and yeah, you can actually kind of wring out. You've lost the moisture, so you no longer have moisture to actually generate precipitation. And I thought of another one that I'm blanking on right now. So those are some good mechanisms for losing that snowpack at that higher elevation.
Physical characteristics of the atmosphere
and or the landscape.
or the landscape.
Yep. Yeah. So, but it's cool that you see it at a lot of places, and we actually have something that I didn't have time to talk about. We've flown LiDAR, so I think that you guys have heard about that in here before, but it's essentially just, sending lasers down, collecting the returns, and getting a map of the landscape. Well, we did this before there was snow on the ground and after there was snow on the ground to actually get a measurement of snow depth. And then we went out and did a bunch of density measurement, and by we I mean a whole group of other people, so I wasn't actually involved in that part of the collection. So there's measurements now of the snowpack, the snow depth, and some estimate of its water equivalent, although that's slightly less certain than the depth itself. And so we actually have this for a number of watersheds throughout the West, and it matches the SNODAS model data that you see here surprisingly well. So that's really encouraging that this isn't crazy. Yeah.
Does the Sierra model follow the same pattern?
So yeah,
I'm not sure everybody can hear that.
Oh, does the Sierra model follow the same pattern? I think I understand the question, which is, do we see this in the Sierra as well? And a couple of our LiDAR flights were flown in the southern Sierra and some watersheds sort of upslope from Fresno. And that matches pretty well as in Tuolumne. So it's promising.
I've got a question.
Yeah.
1 degree, 2, 3, 4, 5 degrees Celsius.
Mm-hmm.
If you took average estimates by the IPCC, which is the scientific standard today, when do you think those changes would occur? How far out into the future?
So that gets us about a century out.
For the 5?
Yeah. Plus or minus a lot of uncertainty.
Yeah.
Excuse me, sorry for the cough. Yeah.
I noticed here when there's no clouds comment on how the effect of having less precip and clear skies and then colder temperatures?
Yeah, clouds are really important. There's no question. They affect the radiation balance and they, how much is getting in, and then they also affect how much is leaving, how much of the energy that's at the land surface is re-radiating out. So I would say they matter a lot, and that's not something that I'm working on, but there are a lot of people who definitely are working on clouds and trying to understand cloud formation and whether or not we're going to see kind of a feedback by which clouds have the ability to help reduce some of the impacts.
Yeah, feedback stuff.
Exactly. Yeah. So.
They carry the moisture.
And they carry moisture. Yes. they're important on a lot of different fronts. Yeah.
Building on that, do you have information on the amount of snow cover over a large area versus temperature over that area? Do we get, if you have a lot of snow cover, you have a large albedo,
yes.
So you get reflected sunlight and it doesn't give as much. Is that the case?
So I actually haven't seen numbers. I should look this up. I don't know the answer for changes of the albedo effect in mountainous terrain. Yeah. Certainly a big impact in the Arctic, and there are folks who are definitely including that.
Maybe in the plains, but here we have a lot of trees.
Yeah.
And those kind of disrupt that albedo.
They definitely do. The only work that I've seen is on a much smaller scale, where it's looking at different harvest patterns. So if you have like honeycomb harvesting versus strip harvesting versus larger patch harvesting of timber, what impact that has on kind of local scale energy balance. And so it does have an impact in terms of what the, how quickly does the snow melt off and how much snow actually accumulates in those gaps between trees. So that's a little bit different scale though than the answer that I think, or the question that you were asking. Yeah. Yeah.
So I was wondering, I don't know that I heard every question, but didn't you say at the beginning something about wind increasing? And then how would that work with all of these? As wind blows snow in, or doesn't it increase friction and temperature, and wouldn't it change all of this if the winds do increase on average?
So winds can do a bunch of different things. They can bring in vapor. They can bring in moisture. And so that's one of the things that's been invoked actually to describe why there's this mismatch between what we think precipitation has been and what streamflow is measured to be that's integrating across this wide range of elevations. So that winds, the upper elevation winds have actually increased and are bringing more moisture in from the Pacific. So that's pretty cool. Winds can also, a warm wind can melt snowpack just like that, it's just moving, especially if it's dry enough air, it can move dry, warm air across and melt off a snowpack. During storms, wind can play a particularly important role in moving unconsolidated snow that's not yet in the snowpack into drifts, or scour certain areas free of snow. And so that can have a pretty big impact, well, not only on roads and where we're driving and whether you're going to drift that blocks your driveway or something awful like that, but where you have to just keep shoveling and shoveling. But they have a big impact on how we measure how much snow we think we have. And so measuring both in and out of drifts can be really, really important. But typically, the drifting doesn't persist indefinitely. Usually you start to develop either a sun crust or a wind crust that will help to solidify that pack. The other thing that is really important is that our gauges, not the SNOTEL sort of pillows on the ground, but the ones that are either small units, like little buckets that are recording wind, and sometimes they have flaps around them. Those can be really, really bad at catching precipitation if it's very windy out, particularly if that precipitation is either snow or mixed precipitation. And so there's a lot of effort that goes into trying to dampen. The reason for those little flaps around it is to dampen the wind so that the precipitation can actually fall vertically into those buckets so that we actually measure what's really falling. So that's part of why the SNOTEL sites developed the technique that they did, so that we get as accurate an estimate of what's on the ground as possible. And saying those is a really important, don't put them right in a drift and don't put them right in an area that gets scoured. Yeah?
One thing you haven't mentioned is sublimation. So what's in the literature about this? I mean, there's always, you freeze something and right away there's always something that's going right from solid to vapor.
Right.
So that could change a lot with increase in temperature.
So yeah, so the question was about sublimation and the loss of water from the snowpack, not just through melt, but also directly back up to the atmosphere. And that's not something that I talked about a lot. And is that going to change? It's likely that it could shift some. The models that I've run for the Sierra suggest that it's not as big an influence as we had thought. So whether those models are right or not is another question. So typically, people are looking at trees and the role that trees play in transpiring water as being more important often, but not always, than direct evaporation from the ground or a snowpack. And so the real question is, at what temperature will trees in any particular region start to really turn on in winter? And so there's recent work in the southern Sierra that suggests that trees there are cranking a lot more during the winter than we had previously thought. They're actually transpiring much more. That's not the case across all of the West, but apparently it is warm enough and there's enough radiation for it to be, and enough moisture in the winter for it to be worth it for at least some trees that are at colder temperatures than we had previously thought. So there's more to be done there. You want to start measuring it. I'm sure that people would be game to see what you find. Yeah.
So can you talk about what the effect on tree line might be? Because the temperatures are going up, but moisture is changing.
Yeah.
And then trees being higher might actually help keep snow.
Yeah. So,
I'm not sure if I heard that.
okay, I'm actually going to go back. Let's see if I can guess what slide this is. Okay, so I didn't talk about this earlier because I figured that there was a lot already, but so across the top, that black line there is at the very top. That black solid line shows the range of evergreen trees. So the typical elevation range of evergreen trees, with the triangle being the average, so the median. And so so those trees occur during that, or in that elevation range, when the snowpack is increasing really dramatically with elevation. And so there's been some work that's been done by folks in Colorado that suggests that region where evergreen trees are most active could be one of the most sensitive regions to warming. And we might keep an eye on greenness, so NDVI, a vegetation index, to say how green trees are as a way of evaluating their response to changes in snowpack. And so they've looked at this over the course of wet and dry years to suggest that you do see some response. It'll be interesting to see whether or not this plays out into the future, as if there truly is less moisture available or that moisture occurs earlier and maybe is either infiltrates or runs off or potentially is used by trees earlier, how that will shift summer productivity by those trees and their ultimate, sensitivity perhaps to drought conditions or to invasive insects or other things. So does that help?
So you think tree line would stay the same or go down or?
That was complicated. I think that in some places it may move up. So there's some observations in the Salmon River Basin, for example, where there have been more intense fires, that there's relatively little seedling recruitment. So trees are not getting replaced after following these fires. There's the suggestion that that's because the conditions aren't really very good right now for the seedlings to succeed, and instead they're more favorable for like a sagebrush steppe kind of ecosystem to be more established and successful in areas that have previously been, you know, either Duffer or ponderosa. That's a hypothesis at this point that that we'll see whether that bears out. So it's possible. Other places, I think that you do see, you do see establishment following a disturbance, and you do see trees succeeding. So, so I don't think that would be the case everywhere.
All right. Sarah's now turned off, so all she wants. A couple of things really quickly here for thank Sarah finally again. Is in about 2 weeks' time, the first Tuesday in February, we have Aaron Linsdow, who talked already here as part of the Mountain Festival about skiing across Antarctica. He's going to talk more about